This video, we're going to talk about 4.3, which is subspaces of vector spaces. And I started to talk about this a little bit at the end of the last video, but I'm going to give this formal property here. If capital W is a non-empty subset of a known vector space V, then W is a subspace of V if and only if, meaning that it's sufficient to say these two things. For all U, V, that are elements of capital W, then U plus V is an element of W. So closed under vector addition. Two, for all U in W and C in the real numbers, C times U is in W. That's closure under scalar multiplication. Okay, so you just need the two closure axioms of the 10, which were number 1 and number 6 of our list of 10, as long as you know that W is a non-empty subset of the known vector space V, and we have the list of known vector spaces from the last section that we're going to be thinking about this time. So n by n matrices, n by m matrices, polynomials of degree n or less, Rn, those sorts of things. So let's go ahead and look at number 1 as an example here. So we want to verify that W being the set of all x1, x2, x3, 0, and tuples with x1, x2, and x3 are elements of the real numbers is a subspace of R4, that this is fourth degree. So we would need to first say W is a non-empty subset of R4. It contains at least one vector. I can see the 0 vector right off the top of my head. 0, 0, 0, 0 is in W, so it's non-empty. So we can just go ahead and say is W1 is going to be x1, x2, x3, 0. Say W2 is equal to y1, y2, y3, 0, something like that. W1 plus W2 equal to x1 plus y1, x2 plus y2, x3 plus y3, and then 0 plus 0 is 0, which is in W. So we have closure under vector addition. And then we have C times x1, x2, x3, 0 is cx1, cx2, cx3, 0, which is also an element of W. So we have closure under scalar multiplication. Therefore, W is a subspace of R4. All right, let's go ahead and look at number 3. And we're told W is the set of all 2x2 matrices in the form of zero, A, B, 0, where A and B are real numbers, and the vector space, the known vector space that we're testing to see if this is a subspace of is M22. So I see that it's non-empty because it contains the 0 vector. So we can say it's a non-empty subspace or subset of V. And so we just test the two axioms here is 0, A1, B1, 0 plus 0, A2, B2, 0, which is equal to 0, A1 plus A2, B1 plus B2, 0. That is in this form. So that's in W. So we have closure under addition. And we have C times 0, A, B, 0 is 0, CA, CB, 0, which is in this form. So it's also in W. So W is a subspace of M22. Let's go on to number 5 here. 5 requires some knowledge of calculus. It says W is the set of all functions that are continuous on -1, 1, the closed interval there, and V is equal to the set of all functions that are integrable on -1, 1. So capital C refers to sets of functions that are continuous on a particular interval. I don't know that I have an abbreviation for integrable functions, But if you remember from calculus, then we have call from calculus, probably calculus 1 for you, that continuity implies integrability, making W a subset of V and a proper subset of V. And it's non-empty because we could think of the zero vector, or y equals 0, has to be in there. W is non-empty. So we just need to show that 1, if I have F plus G is in W. So let's think about that. If I have a sum of continuous functions, is that continuous? Yes, because the sum of continuous functions on a closed interval sum of functions, say it this way, functions continuous on a closed interval is continuous on that closed interval. We're just adding or adding y values together, and there's going to be a y value for each x value, each and every x value in that interval, because there's no jumps, asymptotes, or holes in that closed interval. So every single x value from -1 to 1 inclusive is going to have a new y value, and it's going to be continuous. It's not going to cause any new jumps, breaks, holes, asymptotes, things like that. Part 2, C, F will be in W because the product, because the scalar product of a continuous function on a closed interval is a continuous function. This is a non-rigid transformation. This is just all we've done here is stretch or compress the graph, but we haven't made it discontinuous in any way. So we are, this here is addition of functions, which you have done, and that doesn't change continuity at all. So just bringing that back from calculus 1 there. And let's go on to number 15 here. So we're told in number 15 that W is the set of all matrices in 3 by 3. So W is the set of all matrices in 3 by 3 that are 1AB, C1D, E, F, 0, A, B, C, D, E, and F are real numbers, and show that W is not a subspace of V. V is M3, 3. Show W is not a subspace of V. So let's go ahead and check for under vector addition, we would have a problem. Either one of these, but let's just see if this is closed under vector addition. So if I have 1, A1, B1, C1, 1, D1, E1, F1, 0, plus 1, A2, B2, C2, 1, D2, E2, F2, 0. Then I'm going to get 1 plus 1 is 2, A1 plus A2, B1 plus B2, C1 plus C2, 2, D1 plus D2, E1 plus E2, F1 plus F2, 0, and that's not an element of W. It's not closed under vector addition. So it automatically fails. Another thing you might have done is you might have taken the number 2 times something like 1, 0, 0, 0, 1, 0, 0, 0, 0, just to be a little bit more specific in our counterexample. I didn't need to be this generalized here, but that would make 2, 0, 0, 0, 2, 0, 0, 0, 0, which is not in W, so not closed under scalar multiplication. So if it fails either one of the two conditions, it's not a subspace. So we've shown both of them fail. Here, it's not a subspace. So let's go ahead and look at number 19 next. 19 says W is the set of all vectors in R2, whose second component is the cube of the first. So W equals the set of all x cubed, x being an element of the real numbers. And V is equal to R2. And we want to show that that is not a subspace. So show W is not a subspace of V. Okay, so let's think of some examples, like if I have 1 and then 1 cubed is 1 plus 3 and then 3 cubed is 27. And I add them together, that's going to give me 428, but 4 cubed is 64, not 28. So this is not in W, so it's not closed under addition. It's really all that I need to see there. So it's more than enough. Let's go on to number 23, which asks us to determine whether this is a subspace of all continuous functions. So the set of all even functions I'd have a problem if they said the set of all odd functions, because the zero vector is not an odd function, but it is an even function. And all constants are even functions. So I have all of the scalar multiples in there as well. So an even function is f of x, f of negative x is equal to f of x, just to remember what an even function is. So, and v is equal to all continuous functions. So is this a subspace? It is. W is a non-empty subset of V. The even functions that are in from V are continuous functions. That's right. So, and we are going to have an even function plus another even function is an even function. We're not going to add any terms that are going to make it odd. So W is closed under addition and scalar multiplication. Remember that what makes something even is that it has y-axis symmetry. So taking a scalar multiple of it is not going to change the y-axis symmetry at all. That there's still going to be an f of 0 that lies on the y-axis, and everything will be symmetric to that. So it's closed under addition and scalar multiplication. Therefore, W is a subspace of V. All right, that is it for that video, and we'll come back next time to talk about section 4.4, which is spanning sets and linear independence. That's really an important idea moving forward. Also, we're going to kind of have this an extension of this idea in differential equations, where we want to talk about fundamental sets for a solution set that where our components are not just vectors or but they are functions. But there's a lot of extensions of these linear algebra concepts into differential equations, and this idea of linear independence between our functions that are within our fundamental set in differential equations will come up quite a bit. But let's start here and in 4.4 next time and talk about how to prove that a set of vectors spans a space and how to prove that those vectors are linearly independent. See you for the next video.